Hello students, Shine is here. We are here with one of your practicals for ARC 211, that's the mechanics of a structure. And in this practical, we are exploring the truss structures from analytical and experimental point of view. So the truss which is used in this experiment is a Gothic truss. The reason this truss or two-dimensional truss, which is generally used in the roof structures, has this unusual shape is to provide more space in the area near the attic, so people can use that space for living. So if there is a straight member in the roof structure, the spacing would be only limited to the middle part, but when you make that hunch, if you like, it's making the attic space more spacious and more livable. Alright, the price that we're paying for that kind of modification is analysis of this truss becomes more complex from closed form solution point of view. So in this experiment we want to construct a certain Gothic truss, apply some load and predict the amount of the load that would develop inside each member given a loading scenario to one joint, and then using a combination of closed form solution, hand calculation, or web solution and experimental measurement. You want to complete all these methods and compare the results which are obtained by each. Okay, so this structure, I first go through the document which is available to you as a lab instruction. So this only provides you the background information. Your report will be written in a separate document which is called report template. I will show you that document later on. But as you see, this experimental setup, it has two compartments. In the first area, that is where you assemble your two-dimensional Gothic truss, and when you fix that on the left to a pin support and right hand side to a roller support. So here on the right you see that there are some room for horizontal sliding, and every joint member can be used for applying a load with any angle you want. So the angles are adjusted by moving the sliders, and the loads are applied through a cable going through the pulley, and eventually the amount of load is by adding drop weights. So you can see this is a flexible configuration. You can change the loading node, you can change the angle, and you can change the magnitude of the load. And on the left hand side there is a vertical space which helps you to put a selected member and apply a load to the same system by cable and find out that what is the limit of that member. So by increasing the drop weight, you increase the load, and eventually at one certain load this member is going to be collapsed. But the collapse is not just making the member going to failure. This is a concept which was developed by myself and former technicians in the unit, Mr. Bernard Kozil. So this involved using a collapsible member or magnetic member, and in that we are replacing each member by a corresponding collapsible member. So these collapsible members are holding magnets between them, so the length doesn't change. So for example, in this case you can take away the middle part and replace it with that collapsible member. So geometrically nothing is going to change, but when you apply the load to the structure, provided that this member is under tensile load, the magnet is going to simulate the collapse, the failure under the tension. So this truss has a limitation. It can only measure the tensile load, not compressive load, but for educational purpose this is enough and proved to be practical. Alright, so what you need to know from this instruction is, first, you will be given a loading scenario. The loading scenario is announced by myself just during the practical. So in this table 2, I would specify only one row when it tells you load is applied to the which joint and at what angle. And then this, forget about the rest of the rows, only you will be doing one loading scenario. For that loading scenario, the geometry of the truss has been provided to you, so all measurements pre-made, so you can read this. But more importantly, instead of the length of the member, also you have been provided with the coordinates of the member. And one unusual thing here is the nodes are being assigned by numbers, not by letters. That's in contrast with what we do in class. And the reason is you are supposed to use a web solver which only takes, you can construct that virtually on the web application, and for that you need the nodes to be labeled by numbers. So that's why we chose that labeling conventions here. So using these coordinates and the loading scenario which I will provide to you, you can go to a web solver, and the address for this web solver is given somewhere in your document. I think if you go to this page, that is a web solver, right? So once you open that hyperlink, it would bring the online solver, and here you just watch the provided video on how to enter the coordinates and loading this solver, and eventually in this area you would get a graphic and numeric solution for your specific loading case. So this is just one reference. That reference, at the same time you will be doing a hand solution, and also you do some measurements. So all these three study of the structure, they should comply, the results should comply. Some results are, some errors are expected, so you would discuss the source of the error and how they can be minimized. So right, that is the instruction document. Like I said, you'll be provided by a report template. In this report template, you will be completing the name of the participant in a group. That this is a group report, one report per group, and these your address or just response to these questions one by one. Some parts require free body diagram, hand calculation. Some of them, this is just a table you fill in, and if you want to make a graph of the comparison between hand calculation, web calculator, and the measurements, this can be done. This is the editable template you can use. So I quickly put a report which was provided by some students, which typically this is the hand calculation, and these are the web solution, these are the coordinates, the measurements, the averaging, and finding the linearity factor and writing a conclusion. So let me elaborate about the concepts of a linear displacement. So this truss structure is supposed to perform in a linear mode. That means if I apply 10 Newton, there will be some forces developed here. If I multiply 10 Newton by 2, the induced forces in member, they multiply by 2 as well. So if I divide that 10 Newton by 2, make it half, so the developed forces would reduce by half. So as a result, that no matter what force you are applying here, that is all you need to predict in case a load of a different magnitude with the same direction applied to the same joint. And all you have to do is to find a proportionality factor, either a growing factor or a shrink factor, and apply that to your sample solution. In other words, when you do the web solution, you just apply a typical load of 16 Newton with a certain angle. And then by reading the document, you have to find out based on the limit of the magnet which you are going to replace or take it as a collapsible member. So how large you have to increase that 16 Newton to get exactly the collapsible load developed inside the magnetic member. And for that case, you would set up and find out the corresponding drop weight, such that when you apply the drop weight, exactly at that drop weight, this magnet would collapse. So how do you know that the drop weight? Before replacing this member, for example, the tensile force, this one, by a collapsible one, so you measure the limits of the magnet in the left hand side compartment, and then using that value and your web calculation and hand solution, you find a growing factor or shrinking factor between the apply load here, which develops the very same collapse load in the magnetic member. And then you set up your experiment, and by running that, you expect to see something in that range, breaking the system exactly at that collapsible member. So this is the 3D model, nothing very special, except so you can move the hanging point left and right. But if you want to change, for example, you want to apply a load to this joint, right, at a certain angle. If you want to apply this vertically, you bring that slider right at the top of this. Or if you want to apply it at a 45 degree, you have to just keep this one back and forth, such that when you are looking from opposite side, the rope is making a 45 degree with the horizon. And to measure that angle, you can always use any tool convenient. My suggestion is there are some mobile app which let you to read the inclination angle. So they're very handy, so you can use them to replicate exactly the scenario which you were specifying. So left hand side, you just mount the collapsible member vertically. At one end fitted here, the other end you tie the rope. The rope goes through this pulley, goes through all these slots, coming all the way here before a drop weight would apply the load, and you gradually increase this one until the magnet is broken. Once you have that number, comparing this number with the estimated load in this due to the gauge load or 16 Newton, you find the magnification or shrinking factor. That magnification shrink factor will tell you how far you have to go with your drop weight to get exactly the same number of load developed here. So please study the instruction, and if any question, like usual, email me and I'm happy to take your questions. So to give you a close look of the collapsible member, that is how this is being made. Make sure this has some male-female fitting points, so you have to be careful not mounting this in reverse. So when you do this correctly, it would snap tight into each other, and you would have those mating each other, and that they are opposite. If you mount them both magnets the same way, that's not the right. So this is typical for a short member. You can replace any member according to the scenario which prescribed. You can replace any member. If you want, for example, if you want to replace this with the collapsible member, as the technician, he would provide a counterpart for this member which has a magnetic collapsible member in between. And just regarding the experiment setup, this setup was made in Swinburne. That's an intellectual property of myself, and of course I received lots of support from the former technician Bernard Kozel, who is not at Swinburne anymore. But yes, this is, I hope you enjoy this experiment, and that brings your knowledge about the truss structure into a new level. Thanks for watching this introduction video, and looking forward to see you in the lab. Take care and see you. So, bye.